And 9.3, we've kind of exhausted all of our options for solving quadratic equations. And just to illuminate them all again, we've got factoring, we've got square root property, we've got completing the square, and we just have the straightforward quadratic formula. All right, so 4 approaches to solving quadratics. All right, so in 9.3, we're going to take those strategies of solving quadratics and apply them to what I call semi-quadratic equations. Okay, these are definitely not quadratic equations in our examples because there's no x, well, there is an x squared, but the highest power is x to the 4th, highest power is x to the 10th, highest power is x to the 6th. So these are much more complex functions than just a quadratic, but they behave like a quadratic. Not only do they behave like a quadratic, they look like one. Right? This looks like ax squared plus bx plus c, just my powers are off. This looks like ax squared plus bx plus c, just my powers are off. Right? So in these cases, when I have equations that look quadratic and act quadratic, I can treat them quadratic by taking our same sort of steps. So, right, there's a couple different tactics to doing this with some substitution. If you're looking on MathLab, it's going to show you how to substitute to do it. But I tend to think that we have the skills to do it without the substitution. I don't think we need to. So, right, what I'm going to do in each of these cases, so I'm going to set up equation in standard form. In other words, equal to 0. Right, just like I would for a quadratic if I was going to factor or use the quadratic formula on. Right, and all these are already equal to 0, so they're already set up for us. They're already in quadratic form, semi-quadratic form. Okay, and now I'm going to factor. And this could mean, as always, right, when we want to factor, that could mean, right, maybe there's a greatest common factor. Right, maybe we have to, right, unfoil it into our 2 binomial pieces. Right? But I think in all these cases, factoring is going to work, one of these two methods. So we won't have to rely on completing the square or the quadratic formula for any of these. We can just go ahead and try to attempt to factor them. Right? And the trick is, well, they're not quadratic, so it's not going to work out like x plus something, x minus something. Right? But because in all of these cases, notice that the powers are all double each other. Right? 2 times 2 is 4, 5 times 2 is 10, 3 times 2 is 6. That's what puts them in quadratic form, because our standard quadratic our powers are double each other, right? 1 to 2. We probably never thought of it like that, but that's what makes these semi-quadratic in nature, is that the powers are double each other, so it works like a quadratic. So when we factor, right, instead of putting x and x to start, right, when I factor this polynomial, I need 2 terms that are going to go at the beginning that multiply to get x to the 4th. Right? The nice thing about this is that it's always going to start with whatever that middle power is. Right? Because if I multiply x squared times x squared, right, I'm going to get x to the 4th. Right? Now treat it like normal factoring. I need factors of 45 that are going to add up to 14, combined to get 14. And I think that's going to be 9 times 5. And in order for them to add up to negative 14, that would be a negative 9 and a negative 5. We'll treat it the same way as a quadratic. We'll solve each of these factors by setting them equal to 0. So I take this and I say x squared minus 5 equals 0. I take this, and we solve each equation, we can add 5. Right. So everything we've done has been the same thing we would have done for a quadratic. Just with a quadratic, we would have been done. Right? We wouldn't have had this x squared here. It just would have said x equals 5, solution. Right? But now we've got a little quadratic equation. Right? And we can take the square root of both sides. Right? And don't forget, when we take a square root, we're going to end up with plus or minus. So there's 2 solutions from there. And over here, x squared equals 9, square root both sides. And x equals plus or minus square root of 9 is 3. And we've got our 4 solutions to this semi-quadratic equation. We're going to treat them all the same way. All right, so once we factor, set each factor equal to 0 and solve. Right. 1 second.
Yo.
Yo.
What's up, man?
Nothing.
So I know.
Hi, I'm back. All right, so these last 2 we can do same way, quadratic in nature. So, all right, we're going to factor this just like we would a quadratic. I don't see a common factor, so we'll set it up to unfoil it. Okay, but the difference now is that I need x to the 10th at the beginning. So I need 2 terms that are going to multiply to get x to the 10th. And we're going to use x to the 5th and x to the 5th. Right? And again, it's not a coincidence. It's always going to be what this middle term is, the power of the middle term. Right, just like up here we used x squared, over here we're going to use x to the 3rd. Right? But this one is a little bit harder to factor because of the 9. We need to somehow work with the 9 and the 2 to make the 7 happen. And I think this one is going to work out that it is 9x to the 5th and 1x to the 5th. That's our 9 and 1. And then we need to make a 7 happen in the middle. Can't put a 2 back here, that'd be 18. So I think a 1 and a 2 would work out. And that's going to be, if I multiply this out, 9 times 1 would be negative 9 and positive 2. Negative 9 and positive 2 add up to negative 7. So it factors just like a quadratic would. We break it down. X to the 5th minus 1 equals 0. 9x to the 5th plus 2 equals 0, and then we solve each equation using our root properties. We can find all our answers. So x to the 5th equals 1. And from mod 8, we're going to take the 5th root. And the 5th root of 1, well, there's only one number that'll do that. 1, 1, 1. 1 times itself 5 times. X equals 1. Right, notice I don't need a plus or minus. Right, you only need a plus or minus if you take a root that's even, a square root, a 4th root, a 6th root, right, because those are the only values. If I take a value and I square it, it would work for a positive and a negative. 3 times 3 is 9. Negative 3 times negative 3 is 9. Right, but that doesn't happen when I do it to the 5th power. Right, so here, if we're solving this, we'll end up with x to the 5th equals, subtract 2, divide by 9, and then we can take the 5th root of both sides, and x equals the 5th root of negative 2 over 9. There's our solutions there. All right, and lastly, again, it's in quadratic form. I've got powers that are double each other. And And honestly, in this one, the powers wouldn't even need to be double each other. We could do this lots of different ways. It just works out nicely that it looks quadratic. But because these have a greatest common factor, right, this is solvable in lots of different situations. It doesn't have to be exactly quadratic, but their GCF is x cubed. And that'll leave us with x cubed minus 4. And we can set each one equal to 0. And solve each one. Well, the only thing that I can cube to get 0 is 0. This one, x cubed at 4. Solve for x. And we get the cube root of 4. Again, no need for a plus or minus because it's a cube root and it's an odd root. And there's our solutions. So, right, this is my first video on the semi-quadratic. This focused on powers of x that were integer whole number powers. All right, the next video is going to look at ones that are rational exponents, but we're going to do them the exact same way. So nothing really different. I'll just put a few more examples on the board.